So in the previous video we ended with this expression, and before this expression, uh, before we reached this expression, the step before that we had this term. And if you are confused how we got from here to from this term to this term, you will have to understand that this expression is not asking us to find the position vector as seen from the primed frame of reference. R vector is just R vector, and it does not matter from which frame of reference you are describing what R vector is. R vector is the position vector as seen from the unprimed frame of reference. So it's a bit redundant to write sigma prime beneath R vector. All frames of reference agree that the position vector as seen from the unprimed frame of reference is the R vector. So there is no ambiguity about that. And another thing that I wanted to say is that both frames of reference agree on what omega vector is, and therefore they agree on their time derivative. So it is not necessary to write a sigma primed below d omega by dt. We could have as well written a sigma. D omega by dt done with respect to sigma prime or with respect to sigma will yield the same result. So it's not necessary to specify with respect to which frame of reference we are doing this differentiation. In a class, I was asked the question that the angular velocity omega of the rotating frame of reference, if we are talking about the angular velocity of the rotating frame of reference as seen from an observer on the rotating frame of reference, then that person who is on the rotating frame of reference cannot perceive his own angular velocity, and therefore omega as a vector will not make any will not exist for this particular observer who is standing on the rotating frame of reference. Now, is this true? Does the person or the observer who is on the rotating frame of reference, can he not perceive his own angular velocity? The answer is no. He can perceive his own angular velocity, although not in a direct way. This situation is not the same as an observer who is moving with constant velocity or is in a frame that is moving with constant velocity. In this case, the observer is in a non-inertial frame of reference. So he can actually do experiments to find out what his angular velocity is. Because he is in an accelerated frame of reference, he feels all the effects of the forces that arise from being in a accelerated frame of reference. In this case, because this frame of reference is moving with a is rotating with a angular velocity of omega, if an observer places maybe a coin here, he will see that the coin experiences a certain centrifugal force which is given by mr omega square. Now obviously he can measure his r, he can measure his mass, and from the force which he can easily calculate, he can easily find out what his omega is. And also he can throw maybe a ball towards another observer who is standing at a diametrically opposite point, and he will see that the ball deflects in a certain direction, and from the direction in which the ball deflects he can find out the direction of his omega. So he can easily do experiments to find out both the magnitude and the direction of the angular velocity. So therefore he knows what his angular velocity is. Omega does exist for this observer, and not only that, even if omega is changing, he can in theory do such experiments at each point in time, and therefore he can build up a history of omega. And from that he can find out what omega as a function of time is. So omega as a vector does exist for this observer, and this observer will agree as to the magnitude and direction of omega with respect to any other observer who may be standing on the ground. So it does not make any sense to write a sigma primed beneath this term. This term is the same for both observers. So we can easily write d omega by dt as seen from sigma frame, and these two will be equal, and in that case we may drop this suffix altogether and we may write d omega over dt simply. Now consider a specific example in which a particle is moving with constant velocity with respect to the ground. In such a situation, a vector will become 0, and if omega is constant, this vector, this term will go to 0, and we can say that a prime equals this. This is the negative of the Coriolis acceleration, and this is the negative of the centrifugal acceleration. So let us consider one specific example in which a turntable or a merry-go-round is going in this direction, in the anticlockwise direction with angular velocity omega, and if a person tries to throw a ball or some other object to another person who is sitting diametrically opposite to him, this person will see that the ball moves in a curved path like so. Let us try to explain that. To do so, first let us consider the motion of the ball with respect to the ground or an observer standing on the ground. Because this ball is on the turntable, it has a certain tangential velocity at the moment it is thrown, and this velocity is the velocity that is imparted to the ball with respect to the merry-go-round. So the resultant of these two velocities, along that path this ball will move. But why does the ball move in a curved path as seen from someone standing on the turntable? That is because the points which should be on a straight line, the ball does not traverse those points with respect to the turntable, because the turntable is continuously going round and round. The points which should have been on a straight line, those points are not traversed by the ball, and therefore its path curves. The points that are on a straight line with respect to the ground and the points that are on a straight line with respect to the turntable are different. So that is how we can explain that with respect to a person standing on the ground. With respect to a person standing on the turntable, we can look at the direction of omega cross v. Omega is the direction in which the thumb points, and v is this velocity. So omega cross v gives us this direction. But there's a minus sign out here, which means that the ball gets deflected in that direction. So instead of going like this, the ball goes in a path like so. Also, this term acts. Let us find out what the direction of omega cross r is first. Say at some instant of time the ball is here, so r is this vector, omega points in the upward direction. So omega cross r will be a vector which is perpendicular to the plane containing omega and r. So it will be a vector something like this. This will be our omega cross r. This will represent omega cross r, and if we do omega cross r, we'll get a vector in this direction, but there's a minus sign out here. So minus of omega cross r is a vector like this. It obviously represents the centrifugal acceleration. And omega cross v prime, that's a vector, as we showed, it's a vector in this direction. So the ball gets pushed to that side. Therefore, when the ball is thrown straight ahead, it follows a curved path like this. We can also think of another example in which a coin which was placed on a turntable, and if the turntable's angular velocity is increased beyond a certain point, the coin will move out radially in this direction. But in moving out in this direction, it will gain a velocity in that direction. So we'll have a force acting on this because the coin has gained a velocity in that direction. If that velocity is given by, say, v primed as seen from the turntable, or with respect to the turntable, the velocity of the coin is v primed in that direction, then omega cross v primed gives us that direction, the upward direction, but because of the minus sign, the Coriolis force will be acting in the downward direction. So two forces will be acting on the coin, and the coin will ultimately move in a path like this. Imagine another example in which a ball is thrown from the top of a tower, or just dropped from the top of a tower. Let this be our x-axis, let this be our y-axis. If the ball is dropped like so, it will ultimately move in a path like this. You can explain this in a few ways. First is that if you imagine, this is a little difficult for me to show, say this tower is on the equator, and as the earth rotates from west to east, the earth is rotating in this direction with an angular velocity of omega. So the direction of omega is actually, in this diagram, it will be in the upward direction. So if I imagine my earth to be like this and the earth is rotating like this, the omega is an upward direction, and the tower is coming, say it is situated on the equator in a way like this. So if I drop the ball, the velocity of the ball is in this direction, while the angular velocity of the earth is in upward direction. So omega cross v will give us this direction, but because of the minus sign, the ball gets deflected in that direction. Therefore, the ball moves in a path like so. The other way by which we can explain this is that this deflection will obviously be extremely tiny. The other way by which we can explain this is that the ball on the tower, because it has a greater radius, it has a greater tangential velocity. So it moves a greater distance than this point on the earth. Therefore, it will, to this point, it will the ball will seem to move at a slightly deviated path, a path that is deviated on the right. So in any case, we can say that two forces are acting on the ball. One is mg, the other is this term, 2 omega v prime. Omega and v prime are at right angles to each other, so we get a sine 90. So if we just write down the magnitude, it will be 2 omega y dot, where y dot is the velocity in the y direction. So we can also say that as this Coriolis force acts on the ball in this direction, the ball gains a velocity in this direction, due to which another Coriolis force will be acting on the ball, and if you try to figure it out, you will see that that Coriolis force will be in the vertically upward direction, but that will be extremely small, so we can ignore that effect. So the downward motion of the ball will be represented by the usual formulas, which is the double derivative of the y coordinate is simply g, the single derivative will be gt, and y will be half gt squared. Similarly, the double derivative of the x coordinate, that is the x acceleration, is 2 omega y dot. In place of y dot, we can substitute gt, so x double dot is 2 omega gt. Therefore, x dot is omega gt squared. Therefore, x is 1/3 omega gt cubed. So this is a way by which we can measure the effects of Coriolis force. let that wait for this video.